Hello, everyone, and welcome to my presentation today on flood modeling for stormwater infrastructure planning in Pooch Cove, NL, using communal model calibration. So just a little bit about myself. My name is Abena Owusu-Amponsa. I'm currently a PhD candidate at Memorial University of Newfoundland here in St. John's. And I do have a master's in water resources engineering from Belgium and a bachelor's in natural resources management from Ghana. So my research interests are in climate change, flooding, and then resilient infrastructure design. We know that flooding is natural occurrence, and at some point it is inevitable. But besides the loss of lives, people also do tend to lose property as well, besides loved ones. And it's not just people that are impacted by flooding, but also the environment is also impacted by it as well. And so with all of these, through on climate change, and then the frequency of these events are just going to increase much more. And then a more frequent occurrence then is going to be typically what we have the road washouts as well. So then with this problem, we need to find solutions. The possible solution then is to come up with resilient infrastructure design, where we design our systems to be able to handle the projected climate volumes that are going to occur in future. In order for you to say that a system is resilient, you need to sort of assess it. And then we need to be able to integrate not just qualitative forms of assessment, but also quantitative as well. And then the relatively inexpensive way of dealing with our projected climate change volumes would be to update the IDF curves based on the climate change projections. But then with all of these solutions comes some challenges. The first is that usually there are limited resources to any community, even to the society, actually to the world as a whole, to be able to address these challenges. Another challenge that also exists is the modeling expertise to be able to come up with this kind of a design. And it still boils back down to the limited resources where the expertise is available, the money to be able to secure such services is quite expensive. And one other challenge we have is basically something that is common in the field of hydrology, I would say, is that we usually tend to have different scales where you'd have a much more smaller rural community compared to a developed urban center. So we need to be able to if you need to make a decision for these different skills, that also sort of poses a challenge as well. So then for this particular study, what we try to do is to identify the flood vulnerable assets within a small rural community, and then also quantify the impacts that maintenance does have on flooding, because to be able to work for the future, I need to know what the current situation is. So once that is achieved, and then we can go ahead and assess what the potential outcomes would be on runoff volumes as they increase, and also identify cost-effective ways to be able to handle these volumes as they occur in future. So our study area here is Pooch Cove in Newfoundland and Labrador. It is a really small coastal community that is located in the Southeast Avalon region. This particular town, I would say, is prone to flooding, mainly caused by tropical cyclones. That is based on its location in the province. A major challenge for this rural town is that there's no hydrometric or meteorological station data sites available. And I think the closest met station is about 30 kilometers away. And then the closest hydrometric station is about 50 kilometers away. So there really isn't much information available to be able to set up a basic model. And then the current stormwater system in the town right now is not able to handle the flood volumes that they're having, the runoff volumes, I would say. So flooding does occur frequently. And so if under the current conditions, there's flooding occurring, once we have a lot more rainfall, we know that the system is not going to be adequate to handle such volumes. So then the first thing we did then was to go ahead and set up a watershed model for the town. There are different data sets that had to be obtained for this to be done. The first was to obtain a data elevation model. I think the highest resolution currently available from The Canada elevation series is the 4.5 meter resolution. And as you can see from the image, there's quite a huge gradient in here in the town where you have really high elevations at one end and then very low elevations at the other end. The next data that was obtained was the river network within the town from the National Hydrographic data set. And this just shows the major flow paths that were located within the town. Our next data was from the land use zoning map. And the town actually in 2020 went about and surveyed the various land sections that you have within that space, and to be able to identify what the uses are now or potentially what they could be in the future. As you can see from the image, there are some recreational spaces, but then there are a lot of rural sections marked here by the brown. And even with the green section that have been demarcated for residential, most of them are yet to be developed regions. Our next data that we went ahead to obtain was the hydrologic soils. And the reason for doing that was the loss method, the infiltration method that we're going to use in the model setup was the SCS curve number method. And so we needed to identify the hydrologic soils within the region. As you can see so we did obtain this map from the global hydrologic soils from the NASA data set. But as you can see from this map, the region is potentially marked with a moderate to high runoff potential soils. And so this would definitely contribute to some flooding and stormwater management issues. Our next data was the rainfall, and then we're using the 100-year return period rainfall. So we do have the IDF curves, not just for the historic climate, but also for 2 future climate projections as well. Another set of data that I obtained were the images and watermark from Hurricane Eagle. So this is the most destructive storm that has ever hit the island. I think it happened in 2010. And so some of the residents were kind enough to document the flooding that occurred within the region. And so we do have these images, and you would know why I have these images a little bit later on. And finally, we had to go about and then conduct some field surveys where we're looking at the cross sections, the length conditions of culverts, and then ditches as well. As you can see from the images, some of the culverts are in pretty bad shape. And if you look at this bottom image, we have a really small entrance that is draining out into a huge exit. And so irrespective of what the flood volumes are, you would know that whatever is happening upstream of this particular location is very likely to flood. So once we had all of our data sets complete, we went ahead to use the PC-Swim model. And there are a lot of models available, a lot of watershed models, but we opted to use the PC-Swim because it is a coupled hydrologic and hydraulic model. And that sort of makes the model setup easy because of the major drainage channels within the study region. And it's also applicable to not just developed regions, but rural ones as well, which is our case. And it also allows for low impact development assessment, which is the route we were looking to use to address future volumes of climate change. And so once we have our subcatchment features, our rainfall, and then we choose a routing method, we put all of this information into our swim model, and then we do generate some runoff. So to be able to be confident in any model, it needs to have some kind of calibration or validation process done. As I mentioned previously, this particular region has no hydrometric stations in there. And so the calibration for this model was carried out in sort of a 2-step method. The first form of calibration that we use is what is known as the basin transfer, where you usually pick a gauged basin, and where you do have a hydrometric station, but then it also has similar hydrologic features to the one that is being modeled. And you basically compare a ratio of the runoff to the drainage area for the gauged basin and then the modeled one. So this is the formula that you go about using to compute this. Very often, once the hydrologic characteristics are much similar, you'd expect the ratios to also be similar. But some research has shown that in cases, sometimes a difference of up to 3-4 times, difference in ratio is perfectly acceptable. That is often the case where you would find that the modeled region might have a lot of storages such as wetlands that are not explicitly captured by the model. So this was the first step that we used in carrying out the calibration. And then I think we found about 4 to 5 drainage basins that sort of matched our modeled area, and that's what we used. And then the second form of calibration is something that's being done a lot more recently. That is the use of qualitative knowledge. So this is normally done in a series of steps. The first section of this calibration involves some form of informal interviews and workshops with the town residents, where you allow the residents to identify or point out places where they know, since they are underground, locations that would typically flood, whether it's during a regular rainfall event or during a hurricane, and then be able to allow their residents to put in their input and then mark out these regions for us. Once we obtained this information, we coupled this with the flood images that I had showed previously, and then we went back to adjust our model to be able to reflect most of these contents. So once we completed these 2 steps, there was another third section where we went back to the town residents to carry out a binary assessment. We know that usually the binary assessment was based mainly on the Hurricane Eagle. It's been a long time since the hurricane occurred, so we basically allowed residents to let us know if a particular section of town where the model is predicted has flooded actually did flood in reality. And so that was how we went about the model calibration. I do have a few results to share. And this is just a table comparing some of the flood locations as predicted by the model versus what was observed. In some locations, the model and observed do agree. In other places, they were not. And what we found out was that for most of the locations where there was a disparity between the model and the observed, there was usually a couple of errors in the DEM where you sort of have a dip, where in reality, there's no dip. So basically, once there's a dip, the model is treating it as a potential ponding site. But then in reality, that was not the situation. So most of these were rectified within the model that we set up. And once we were confident with the calibrated models, we went about to identify a couple of locations where the infrastructure capacity that they have within the town would become limited under a rainfall event. So when you mention that an infrastructure capacity has limited capacity, it's basically where you're saying either the downstream or upstream or both ends of your system becomes flooded. And so at that point, it's basically not functioning like it should. So we're just showing a couple of them here in this table. And if you'd realize, majority of these are with driveways. And so that is something that the town did find quite interesting. So here I do have a chart looking at our flood extent and then the flood depths under the different climate conditions. Just like we would expect, comparing the flood depth and extent under the current climate to the 2 future projections, you obviously do see the increase in extent and then the flood depth as well. And this is what is to be expected since we're going to have a lot more rainfall occurring in the future. This second image was more to address the impact of the infrastructure maintenance on these flooding extent and flood depths as well. So for this particular result, what we went about to do was to sort of create different blockages within the culvert systems and then look at what the impact would be on the flood extent and then the flood depth. But this was only done under the current climate. There is still an ongoing study. So we're going to look at combining these blockages with the future climate change. But like I said, if you know the situation now, you can sort of project what's going to happen for the future. But interestingly, we found that based on the amount of blockage that occurs within these culverts, the flood depth and then the extent are not quite sensitive to these blockages. Maybe another limitation that I should point out is we're just dealing with blockage in circular culverts. So if the culvert had a different shape, that wasn't considered. Also, we didn't consider probably the ditches and then the river channels as well. That kind of a blockage was not considered in the study. So to be able to identify the flood vulnerable assets within the town, we went ahead to use this flood vulnerability guide to set up, to basically identify the vulnerable assets within the town. And what we do is that we're more interested in regions that are within the risk level 2 up until 6, since risk level 1 is perfectly safe for anyone within the community. So I do have just a couple of sections of the town to show, where we are showing the vulnerability map under the current climate on the left and then future climates on the right. I just have a few sections highlighted. So under the current climate, the section where I have circled in red is perfectly safe. But then in future, we sort of start to see that region move into a vulnerable section. And also we have a couple of sections marked out here under the current climate, which are already under a risk level. But then as you move into the future climate, the risk level just increases. And this is another section of town where the results were actually found to be a bit striking. So if you look at the image on the left, where you have the vulnerability for the current climate, the particular region that I've circled right now is perfectly safe. But once you move into the future climate, you'd realize that the risk level just goes from nothing to a risk level 5. So with this kind of information, if the town is planning to do any developments, this would be some useful information for them, just so they know what to not put in the region or what to if they still intend to. Another section of town is circled here where you do have the different vulnerability sections. And there are quite a couple of regions, but once you move into the future projections, you'd realize that the risk levels for that particular region, the areas increase and then the risk colors also increase significantly. So once we carried out this vulnerability map assessment, the possible solutions that we're looking at for the town was to have these nature-based flood solutions. And so the options that we implemented were in putting in a storage as a wetland system upstream, and also probably some bioswales within the developed sections of town. Once we implemented these, we did realize that our runoff volumes did increase downstream, and then our vulnerability map also did change. We don't have all of those images, but I'm just showing a couple of flow volumes from the various watersheds before and then after you put in the LIDs. And so this is just a way for the town to know that you can actually mitigate or treat your stormwater and then manage it without, you don't always need to go in and then dig up the ground, put in a bigger pipe, but then these nature-based solutions can also serve as a really good option as well. So just some summary points from the study. We did develop a watershed model to be able to quantify flooding within the town of Puchco. And then we used the basin transfer and then the local knowledge to calibrate the model. And then the results of the study indicate that the depth of flooding was quite less sensitive to blockages under the current climate. Some infrastructure elements whose capacity also become limited in the storm of an event were identified. And with this kind of information, it can sort of serve as a guide if the town decides to go ahead and then improve or upgrade some of their infrastructure. You can sort of use the limited capacity duration to serve as a guide in picking the regions you want to work on. Also, majority of the vulnerable storm elements were located in the downstream portions of the watershed, since that is where you do have mainly the residential area set up. And then implementing these nature-based solutions, like we have shown, can really help to reduce the flood vulnerabilities. And then thank you so much for listening. And this is my email if anyone wants to reach out. Thank you.